To understand why a rotating universe implies more than one universe, Poplawski refers to frames of reference. These are sets of coordinate systems that are integral to physics, which allow motion and rest to be measured. Imagine two scientists, Terra and Stella. Each is in their own frame of reference. But Terra on Earth, Stella in a spacecraft traveling past our planet. Terra sees Stella's frame of reference moving in relation to her own, which is at rest. Stella, meanwhile, sees her frame of reference at rest, while it is Terra's frame of reference in motion as the Earth races away. Poplawski pointed out that if the universe is rotating, then its frame of reference is rotating. And that only makes sense if it is rotating in relation to at least one other frame of reference. If the universe is rotating, it must rotate relative to some frame of reference corresponding to something bigger, he continued. Therefore, the universe is not the only one. It is a part of a multiverse. Because all black holes form from rotating objects, such as rotating stars, or in the centers of rotating galaxies, they rotate too, Poplawski said. The universe born in a rotating black hole inherits the axis of rotation of the black hole as its preferred axis. In other words, our universe may be spinning in a preferred direction, because that is the way that the black hole it is sealed within is spinning. A black hole becomes an Einstein-Rosen bridge, or a wormhole from the parent universe to the baby universe, Poplawski explained. Observers in the new universe would see the other side of the parent black hole as a primordial white hole. The motion of individual galaxies in that baby universe will be affected by the rotation of that universe, Poplawski said. That's something astronomers are starting to see. Of course, that means that every black hole in our universe is a doorway to another baby cosmos. These infant universes are protected from investigation by the event horizon of their parent black holes, which prevents any signal from being received from the interior of a black hole. Likewise, a trip through this cosmic doorway would be impossible for a budding multinaut, due to the immense gravity surrounding a black hole, which would give rise to tidal forces that would spaghettify such an intrepid explorer. Dark energy puts scientists in a spin. Energy is a placeholder, name given to whatever force is causing the universe to expand at an accelerating rate. Dark energy currently dominates the universe, accounting for 68% of the total cosmic matter-energy budget. This wasn't always the way. During the universe's earliest epoch, it was dominated by the energy of the Big Bang, causing it to inflate. As the universe entered a matter-dominated epoch ruled by gravity, this inflation slowed to a near stop. This should have been it for the cosmos. But around 9 billion to 10 billion years after the Big Bang, the universe started to expand again, with this expansion accelerating, leading to the dark energy-dominated epoch. To understand why this is such a worrying puzzle, imagine giving a child on a swing a single push, watching their motion come to a halt, and then, for no discernible reason, they start swinging again. And this motion gets faster and faster. Dark energy would emerge from the centrifugal force in the rotating universe on large scales, the theoretical physicist explained. If the universe were flat, the centrifugal force would act only in directions perpendicular to the preferred axis. However, in Poplawski's black hole theory of cosmology, because the universe created by a black hole is closed, moving away in any direction would eventually lead to coming back from the opposite direction. That would mean the centrifugal force arising from a spinning universe becomes a force acting in all directions, away from the universe, as parent primordial white hole. The magnitude of this force is proportional to the square of the angular velocity of the universe and the distance from the white hole, Poplawski said. This relation takes the form of the force acting on a galaxy due to dark energy, which is proportional to the cosmological constant and the distance from the white hole. Therefore, the cosmological constant is proportional to the square of the angular velocity of the universe. To provide some further evidence of Poplovsky's concept, more data on the bulk flow of galaxy clusters and on the asymmetry of galaxy rotation axes are needed. This would help further confirm that our universe is rotating. Additionally, more data regarding how dark energy depends on cosmic distances and the progression of time in our 13.7 billion-year-old cosmos could help validate whether the weakening of dark energy is related to the decreasing angular velocity of the universe. The next step to advance these ideas is to determine the equation describing how the cosmological constant generated by the angular velocity of the universe decreases with time, and to compare this theoretical prediction with the observed decrease of dark energy. Poplovsky concluded. This research might involve searching for the metric describing an expanding and rotating universe.